Okay, we are now on the last part of the course, no? So this is the first topic for reactions of nucleophiles. Okay, and this is nucleophilic aromatic substitution. Okay, normally the benzene undergoes electrophilic aromatic substitution, no, or electrophilic attack because of the pi electrons. Okay, so benzene therefore is acting as the nucleophile. However, benzene can also undergo nucleophilic substitution if the ring contains a lot of electron withdrawing groups. Okay, that's why in electrophilic aromatic, the rate of the reaction slows down if there are electron withdrawing groups. In fact, Friedel-Crafts alkylation and acylation will not occur if the benzene has electron withdrawing groups. Okay, so the more electron withdrawing groups, the lower the tendency for the benzene to undergo electrophilic aromatic. Then therefore it has a greater tendency to undergo nucleophilic substitution. Okay, so to illustrate that, now given the following degree of substitution, okay, the nucleophile that is usually replaced in benzene is the halogens because they are very good living groups. No, they are weak bases, so they are not strongly attached to the carbon, so they can easily be replaced. So if you have, for example, an electron withdrawing here, nitro is a very good electron withdrawing group. No, compare that with two electron withdrawing groups. You have nitro here and another nitro here at the para positions. Okay, or you have three electron withdrawing groups. Okay, you have two at the ortho positions and one at the para position. So the atom that will be, or the nucleophile that will be replaced here, of course, will be the halogens. So you can see the ease of substitution, no, based on the reaction conditions. For the first example, wherein you only have one electron withdrawing group, if you react this with, if you substitute the chloride with hydroxide nucleophile, okay, the pH should be very high, like pH 14, and the temperature should also be very high, okay, to have the substitution reaction to occur. So this one becomes OH, and the chlorine as chloride is replaced. So that's why you have nucleophilic substitution. The more electron withdrawing groups, the milder the reaction condition. So this would be about 100 degrees. And you have the phenolic compounds, wherein you have the two nitro here. And finally, if you have three electron withdrawing groups, this can occur at about neutral pH and about 60 degrees Celsius. So you can see the decrease in the reaction conditions needed for the substitution to happen. Okay. And you would notice that in nucleophilic aromatic substitution, okay, the substitution can be enhanced if the electron withdrawing groups are positioned at the ortho and para positions, like here. Why is that? Now, of course, there is a reason for that one. Okay, if you have the electron withdrawing groups, take note that the rate of the reaction is always dependent on the activation energy. Okay, and to illustrate that in our first example, if you have an electron withdrawing group at the ortho and you have the nucleophile replacing that, okay, that will not be replaced directly. We have to look at the intermediate. When the nucleophile attacks that, the pi electron has to move to give way for the attacking nucleophile. So you will come up with this intermediate, okay, wherein you have the chlorine here and you have the nucleophile attached and you have the nitro here and you have the negative here, which is the pi electron. So in other words, the intermediate for nucleophilic aromatic is a carbon ion, okay? So just like carbonium ion for electrophilic aromatic, electron donating groups can stabilize a carbonium ion, right? So that's why the rate of electrophilic aromatic substitution uh, is enhanced, is increased. In nucleophilic aromatic substitution, the intermediate is a carbon ion, a negative carbon, as illustrated here. So what group can stabilize a negative charge? Of course, electron withdrawing groups, just like the nitro. And if the electron withdrawing groups are positioned at the ortho and para positions to the chlorine, you would notice that the negative is very close to the electron withdrawing group, meaning it is more stabilized, okay, than placing the electron withdrawing group at the meta position. No? So that's why here, since the nitro are located at the ortho and para positions, indicates that the intermediate, which is a carbon ion, will be highly stabilized, okay, compared to the meta position. So to complete this reaction, of course, the pi electron, the negative charge has to return and displaces the chloride, okay, forming the final product where the aromaticity is recovered. You have the 3 pi bonds again, but this is already OH. You see that? Okay, so there. So that is the mechanism of nucleophilic aromatic substitution. Okay, and take note that if the electron withdrawing groups, okay, the stronger the electron withdrawing groups. No, we already categorize electron withdrawing groups as strongly deactivating, no, moderately and weakly, right? Okay, so in nucleophilic aromatic substitution, okay, the strongly deactivating, okay, groups like nitro will be will enhance, no, the rate of nucleophilic aromatic substitution, okay, but of course it will slow down the rate of electrophilic aromatic substitution. Okay, that's the difference, no? And the more deactivating, the faster the rate of nucleophilic aromatic substitution. Okay, and in terms of orientation of the electron withdrawing groups, if they are positioned ortho or para to the leaving group like chlorine here, then it will add to the increase in the rate of nucleophilic aromatic substitution. Okay, so for example here, okay, if we're going to look at the reactivity, no, of different reactivity to nucleophilic aromatic substitution. Okay, let's say you have benzene here, and then you have chlorine, no, or any halogens for that, no, and then you have chlorine again, but this one is, say you have a nitro here, okay, and then you have chlorine, with say cyanide here, okay, and if all of this, no, will undergo nucleophilic aromatic substitution, okay, increasing, okay, increasing reactivity. So the least reactive here, okay, will be 1, because this is nucleophilic aromatic. And the second to that one would be 2, because cyanide is less electron withdrawing, okay? And the best would be, 3. The best would be 2, because NO2 is the most electron withdrawing groups. So that's why you have the trend. Now, supposing you have this one here, you have chlorine, and then you have bromine, okay? You have NO2 here, you have NO2 here. So they differ only in terms of the leaving group, okay? So which one is a better leaving group can easily be replaced, and that is the bromine. So therefore, this one will be less reactive to nucleophilic aromatic, okay, compared to a compound that has bromine, okay? Another case is if you have, for example, you have bromine here, and then you have a nitro here, and then you have bromine, and then you have the nitro at the meta, okay? And these two will undergo nucleophilic aromatic, okay? This will be faster because the intermediate, remember the intermediate, as you can see above, is stabilized at the ortho and para positions. So here you have the nitro at the ortho that will stabilize the carbon ion compared to the meta. So therefore, the first one will be faster in terms of kinetics. Okay, now let's look at some important reactions of nucleophilic aromatic aside from this one. One is you have the diazonium reaction is very important in nucleophilic aromatic substitution. Okay. Now, diazonium salt has this structure. Okay, which we can condense into this form. There. Okay. Now, there is another structure of diazonium, resonance structure. Look at the first one. This is the resonance structure of diazonium, wherein the plus will be at the end. There. Okay. So this one, this resonance structure of diazonium will undergo nucleophilic aromatic substitution. Okay. While this one, okay, will undergo, will act as electrophile in electrophilic aromatic substitution. Okay. This is for the synthesis of dyes. Okay. So for now, we look at the reaction of diazonium in nucleophilic aromatic substitution. But first, how is the diazonium reaction produced? No? Diazonium, okay, can be produced from aliphatic amine, primary amine, like methylamine, no? Or from aromatic primary amine. There, okay. If you react this one with nitrous acid, okay, nitrous acid is produced from in situ, just like the Lewis acid, remember, Fe plus hydrochloric. Nitrous acid can be produced by mixing sodium nitrite and hydrochloric acid. So when you mix this in a test tube and you drop methylamine, your methylamine will become methyl diazonium salt. Okay? But the aliphatic diazonium salt is very unstable in water. No? Okay? If there is water here, this will be converted to methanol plus nitrogen gas. Okay, that's that is the product. Okay, that is expected for aliphatic diazonium salt. Okay, now that's why for synthetic importance, the diazonium salt is usually produced from aromatic amine because the resulting product is quite stable. So if you react this with nitrous acid, you will have the diazonium salt. Okay. And you notice in the first reaction for aliphatic diazonium, the nitrogen gas, okay, easily leaves the carbon. That's why your carbon here becomes positive. So it takes up the OH of the water to form the methanol. So the same thing will happen here. When the diazonium salt is formed, this electron of carbon will be taken up by nitrogen, and this will evolve as nitrogen gas, leaving your carbon in benzene positively charged. That's why this can be attacked by nucleophile. So in a way, you have nucleophilic aromatic substitution. Okay. So for example, in Sand-Meyer reaction, okay, Sand-Meyer utilizes copper salts like copper chloride, okay, copper bromide, and copper cyanide. Okay. In cuprous chloride, the nucleophile is the chloride. The copper is just acting as a catalyst. So replacement of that will generate chlorobenzene. So this is another way of producing chlorobenzene. we can produce chlorobenzene from electrophilic aromatic substitution, right? By halogenation reaction. We can also produce through diazonium. And it's very neat, no? Very neat process. Here you will have bromobenzene, okay? And the third reaction is very important because we cannot attach a cyanide in electrophilic aromatic substitution. Based on the 5 basic reactions, we cannot. But it can be attached directly because this is a nucleophile cyanide ion. So it can be attached here. So you have now cyanobenzene. And there are 2 important reactions of the cyanide. If you add water under acidic condition, the cyanide will undergo what you call hydrolysis, meaning reaction with water, converting the cyanide to carboxylic acid. So this is another way of producing benzoic acid. We can also produce benzoic acid from toluene, right? Remember? Through side reaction with potassium permanganate. Now, the other important reaction of cyanide is reduction. So if you add a reducing agent like lithium aluminum hydride is a very good reducing agent, followed by work up with an acid to complete the process, that triple bond, okay, will disappear. The 2 pi bonds will be reduced by the hydrogen coming from lithium aluminum hydride, producing an amine. There, okay? So this is a very important reaction of the cyanide. So you can also call that side reactions, if you will, okay? So what other important reactions of the diazonium salt, aside from the Sandmeyer reactions? Well, the iodine, remember, it cannot be attached to the benzene by electrophilic aromatic substitution because it's less reactive than chlorine and bromine. But here, okay, if you have a diazonium salt, you can add potassium iodide. So the iodide, okay, can easily replace the nitrogen gas, producing iodobenzene. Okay, so there. Now we can also react diazonium salt with water, neatly producing phenol, and the byproduct will always be hydrogen gas. So you see, these are substituents that cannot be attached directly by electrophilic aromatic. So we can attach iodine, we can attach hydroxyl group, we can attach cyanide group through diazonium salt reaction. We can even attach a methoxy group. Say you react this with sodium methoxide. Your methoxide is the nucleophile that can replace the nitrogen. So you produce an anisole. Okay. So this is another substituent that cannot easily be attached through electrophilic aromatic. Okay. Another important halogen which we cannot attach because it's very reactive is the fluorine. But through diazonium salts, if you use hydroborochloric acid or HBF4, okay, the fluoride here can displace the nitrogen, producing fluorobenzene. And this is the way how we can attach the fluorine, not through electrophilic aromatic. Okay, we can even convert the diazonium back to benzene using H3PO2. Here, the hydrogen can replace the nitrogen gas, producing back the benzene ring. Okay, so these are important diazonium reactions. Okay, and they have important bearing when it comes to uh, positioning of the substituents attached to the benzene ring. For example, here, if you are going to synthesize, say, starting from benzene, you want to synthesize this. You have a bromine, you have a bromine here, and you have a bromine here. Okay. Now, if you notice the product here, the bromine are attached at the meta positions. And you know, bromine are orthopara directors. Okay. So if you attach one bromine plus by electrophilic aromatic substitution, the next bromine should be at the ortho and para positions because they are orthopara director in electrophilic aromatic. So you will not end up with bromine at the meta positions. Okay. So how can we synthesize this? Well, if we can attach a group here, if we can attach a substituent here, okay, if there is a substituent here, you notice that the bromine now are at the ortho para positions. If there is a substituent here attached, but that substituent should be removed to end up with the product. Meaning you place that substituent in order to attach the bromine at the ortho and para positions, and then later on remove that. Okay, so that technique can be done through diazonium process. Look at this reaction. Say you start from benzene, and then you subject this to nitration reaction. So this is electrophilic aromatic substitution to form the nitrobenzene. There. So nitro is an electron withdrawing group. Okay. So if you subject this to bromination, the bromine will be meta. It will be here. Meta to the nitro. Okay. But that is a wrong position, as you can see in the product here. The substituent should be at the ortho positions to the, the bromine should be ortho to the nitro, not meta. So we cannot brominate this. So we have to do something with the nitro so that it will become an ortho para director. So the best way to do that is to reduce it using tin in the presence of hydrochloric acid. You can also use iron, okay, with hydrochloric acid, or even zinc, if you want. So the nitro will be converted to aniline because it is reduced. And you know, amino group is one of the strongest electron donating groups, right? So in fact, you don't need to add a Lewis acid here. So if you subject this to bromination in excess, then all the ortho and para positions will be brominated because amino group is an ortho para director. So you have now a bromine here, a bromine here, and a bromine here. So you see that? Okay. So now we have positioned the bromine ortho to the amino group. So all we have to do is remove the amino group. How? Well, you convert that first to diazonium salt by reacting with it with nitrous acid, so that you will have bromine here bromine here, bromine here. And you have the N2 plus, the diazonium salt. Okay. So what reagent can replace that with hydrogen? Of course, H3PO2. So if you react this with H3PO2, then you have now your target product. Okay. Because that part will be replaced by hydrogen. So you have now your bromine here, your bromine here, and bromine here at the meta positions. Okay, so that's why that's one of the important utilities of the diazonium reactions. Okay, now another one, okay, that is unique also for nucleophilic aromatic, okay, is you have the, you call it nucleophilic addition, nucleophilic elimination addition reaction. Okay, so this is the intermediate is very unique. You call it benzyne intermediate. Okay, and this can only happen if you add a very strong base, no? Like if you have here, okay, you have chlorine, no? And you react this, let us say you have a nitro group here, there, okay? So you have the pi bond, the pi bond, and the pi bond, okay? When you add a very strong base like lithium amide, okay, in liquid ammonia, this is a very strong base. The amide is supposed to be a nucleophile, right? So it will remove the chlorine. But what actually happens here is that your amide will act as a base first, and it will remove an acid. That is HCl, right? So the amide here is a base. It will remove the HCl, resulting into what you call a benzyne intermediate. So you have this intermediate. You have the pi bond here. You have now a triple bond here. You call that benzyne, okay? Because the HCl is removed. So after removing the HCl, since this is just an intermediate, to complete the reaction, okay, the amide now, that is the first one is elimination. That's why it's called elimination. The second step is addition, because the amide in the first step, it acts as a base. In the second step, it acts as a nucleophile. So this will attack this portion here. The pi electron has to move, no, and pick up the hydrogen coming from ammonia. There, this is ammonia, right? There. That's the mechanism of the reaction. So you will have now double bond, double bond, double bond. You have NH2 here, and you have the hydrogen here, okay? And you have the NO2 here. But that's not the only product, because if you have this intermediate, you have an alkyne. That's an alkyne, right? It's a triple bond. So your NH2 amide can also attack on the other side here. And this pi electron will move, pick up the hydrogen from ammonia. There. Okay. So you will end up with another product, which is this one. You have the NH2 meta 2NO2. Well, the first one is you have the NH2 para to the meta. So you have two possible products. So you call this benzene reaction. Okay, there. So those are important nucleophilic aromatic substitution reactions. Okay, so now we're done with that one. No? We look at the other resonance of diazonium, which is this structure. Okay, which I showed above. Okay, I said this is an electrophile which can be used in the synthesis of dyes. Okay, so the only requirement is that this diazonium electrophile, okay, can react with another benzene ring, okay, containing strong electron withdrawing group like phenol, okay, or you have amines, no, like dimethylamine. These are very strong electron donating groups. So if you react this, okay, you react this to this will produce a very important commercial product, and you call this dyes. Okay, and you know dyes are colored, they vary in colors, and the variation in color class is due to the conjugated double bonds. You know what are conjugated double bonds? You have double, single, double. Look at that. Look at this product here. Phenol is not colored. Okay. Phenol is not colored. But when you attach that to the diazonium, the double bond, the conjugated double bond is extended. Look at this. Double, single, double, single, double, single, double, single, double, single. See that? The longer the conjugated double bonds class, okay, the greater the tendency for the compound to be colored because it will fall in the visible region of the electromagnetic spectrum. Okay, the electromagnetic spectrum, there are different regions, right? You have the microwave, the radio wave, the infrared, then you have the visible, and then you have the UV, you have the X-ray, you have the cosmic ray. So within the visible region, we can see colors. So this is a dye, okay? So if you react diazonium with this one, okay, that diazonium, which will act as electrophile, okay, will also form a dye. So you have a conjugated double bond also, except that the substituent is not OH, but rather it is an amine. So the color will vary depending on the substituents. Like the left one, okay, will have a different color. I think it's yellow orange, okay, while the right is the blue one, okay. So they are used as indicators, no, in acid-base reactions. They are also used, some of these are used as food dyes, no? The colors of textiles, no? They are synthesized by diazonium reactions. Okay, so that's how significant the diazonium salt is. Okay, so we leave this topic and we move on to the next type of nucleophile reactions, and that is the reaction of alkyl halides and alcohols. Alkyl halides, alcohols, and even ethers. Okay, they undergo what you call nucleophilic substitution reaction. Substitute. There are two types of substitution. Three, no? You have nucleophilic aromatic, nucleophilic substitution at sp3 carbon. So this refers to alkyl halides, alcohols, and ethers. But we also have substitution at sp2 carbon, and that refers to the reaction of carboxylic acid and its derivatives, okay, which we are going to deal with later. Okay, so now we'll focus on these reactions. No? For this reaction, the model is always the alkyl halides. Okay, so we can classify alkyl halides, no, as methyl halide like chloride, or we can also classify it as primary alkyl halide, no, like ethyl. This is primary because this carbon bearing the chlorine is attached only to this carbon. Okay, and we also have secondary alkyl halide like isopropyl chloride because this carbon bearing the halogen is attached to two other carbon, so that's why it's called secondary. And we also have tertiary, okay, because you have three carbons attached to that carbon, so this is tertiary. And then we have two special types of alkyl halides. You have the allyl halide like allyl chloride, and you have the benzyl halide like the benzyl chloride. Right? So these are the common alkyl halides that we encounter, no, in nucleophilic substitution. So to illustrate the general reaction, okay, representing X as the halogen, if there is a nucleophile, okay, now halogens are very good living groups. So they can easily be replaced, no, by other nucleophiles that are stronger than the halogens, no, like oxygen-based nucleophile, hydroxide, methoxide, the alkoxides, no? And then for the nitrogen-based, like amides, no? They can replace the halogen. So that's why it's called nucleophilic substitution reaction. And there are two important mechanisms to describe substitution of alkyl halides. We call it SN2 and SN1 reaction. Okay, so the reaction of alkyl halides can be described in terms of its mechanism, which we have shown already. Okay, that's one. We can also assess their activity in terms of kinetics, okay, and the orientation of the attack. So we call that stereochemistry. And then we also have to look at the nature of nucleophiles that will interact with alkyl halides. And the last one is, of course, the effect of the solvent. So let's look at this, how they affect the two important mechanisms. Okay, so let's start with SN2 reaction. Okay, it is called SN2 because the subscript 2 there would indicate the two reactants that participate in the formation of transition state. Okay, so in SN2 reaction or nucleophilic substitution reaction bimolecular, that's the meaning of the subscript 2, indicates that in the formation of the transition state, there are two reactants involved. And this is very important if you're going to analyze the rate of SN2 reaction. In SN1 reaction, okay, you have nucleophilic substitution monomolecular. There is only one reactant involved in the formation of not transition state, but intermediate state. Okay, because these two mechanisms vary in terms of activation energies. The SN2 mechanism has only one activation energy, so that's why it has only a transition state. So therefore, we can describe the mechanism of SN2 as concerted reaction, meaning one-step reaction. While the SN1 reaction contains two activation energies, one is higher than the other, and the higher is the rate determining step. So since there are two activation energies, we expect two transition states and one intermediate state for SN1 reaction. Okay, that's how we describe their mechanisms. So to illustrate that, let's start with SN2. Let's say you have this reaction methyl chloride. You react this with hydroxide nucleophile. So the overall reaction is formation of alcohol, methanol, plus chloride. So that is nucleophilic substitution reaction. Now let's start with its mechanism. To describe SN2 mechanism, take note that the carbon in methyl chloride is tetrahedral. So we can illustrate it like this. Okay. And since this is concerted and one-step reaction, there is a simultaneous attack of the nucleophile and the leaving of the chlorine. So meaning when the hydroxide starts to attack, the chlorine starts to leave. That is what we mean by concerted. So if we're going to monitor their energies, okay, through energy diagram, say this is the starting reaction, okay, this is the energy, this is the time of reaction, okay, and you have the reactant methyl chloride plus hydroxide. So when the nucleophile starts to attack, it cannot attack the front. It has to attack the back because the chlorine doesn't leave the carbon yet. So you have backside attack. Okay. So when the hydroxide starts to attack the back portion, the energy will go up, okay? Reaching the highest peak, which we call the transition state, before it goes down to form the product, methanol plus chloride, okay? So what happens to illustrate the increase in energy? The hydroxide will start sharing its electron to the carbon, and the chlorine will start to leave. So this one will become partially negative because it is sharing its electron to the carbon. And this one also will become negative because it is still partially attached to the carbon. And the 3 hydrogen will become trigonal planar, like that. So this is a very unstable situation because the carbon is bonded to 5. So that's why it raises the energy up to the critical point, which we call the transition state. So when the chlorine finally leaves the carbon and the nucleophile is finally attached to the carbon, there is the tetrahedral structure is recovered, but there is inversion of configuration, as you can see. And this is very important in identifying SN2 reaction, because if this carbon here, if the carbon here is chiral, in our example, our carbon is not chiral, of course. But if that carbon happens to be chiral and the configuration of this is R, you will end up with a chiral carbon, which is S, because there is complete inversion of configuration. And that is an experimental evidence that the mechanism is SN2. We can check that using polarimeter, right? To identify the degree of rotation, no? Dextrorotatory or levorotatory, okay? So if there is a change in configuration from R to S or S to R, then it is an indication that the mechanism of the reaction is SN2, okay? So that is the complete description of SN2. And if we look at the effect now, or reactivity of alkyl halides, because we have different alkyl halides. Reactivity of alkyl halides towards SN2 reaction, meaning which is the most reactive, the simplest alkyl halide like methyl chloride, or the more crowded alkyl halide like tertiary. Now, looking at the mechanism, this is very important because we can predict, no, if you know the mechanism of the reaction. And looking at the mechanism, you would notice that even with the simplest alkyl halide, methyl chloride, the transition state is already crowded because the carbon is attached to 5. How much more if those hydrogens are replaced with methyl group, like in tertiary? Then you will expect the activation energy to go higher, making the reaction slower. So based on that, we can say that the most reactive alkyl halide to SN2 will be the methyl halide, followed by the primary alkyl halide, followed by the secondary alkyl halide, and the least reactive, of course, is the tertiary. In fact, the tertiary, this one, because of its slowness, okay, will no longer undergo SN2 reaction, okay? So SN2 is usually observed in methyl halide, primary and secondary alkyl halide, okay? As well as in primary allyl and primary benzyl, which we have shown a while ago, okay? So that is in terms of the reactivity of alkyl halide to SN2. Now let's look at we have this one, okay? We also discussed already the stereochemistry. This is part of the stereochemistry effect, okay? How about the kinetics? The rate law, okay? So for SN2 reaction, the rate of the reaction was found to be dependent on the alkyl halide and the concentration of the nucleophile. First order with respect to alkyl halide, and also first order with respect to the nucleophile. So therefore, if you want to increase the rate of SN2, then we have to increase the concentration of alkyl halide or increase the concentration of the nucleophile because they can enhance the rate of the reaction. So that's the kinetics of SN2 reaction, okay? Now let's look at the type of nucleophile that will displace the halogens. In terms of the leaving group, the leaving group could be iodide, bromide, chloride, and fluoride, okay? Like if you have methyl iodide, methyl bromide, methyl chloride, and methyl fluoride. If all of this will be attacked by the same nucleophile, which one is the most reactive? The methyl iodide, the methyl bromide, the methyl chloride, or the methyl fluoride? Okay. Now, we assess the halogens in their ability to leave the carbon based on their basicity. No? The iodide is the weakest base because its conjugate acid HI is the strongest acid in aqueous medium. So therefore, it is the best leaving group. Okay. So since it is the weakest base, it is the best leaving group, then it is the most reactive. So we can therefore say that, the iodide is the best leaving group, followed by bromide, chloride. So therefore, methyl iodide is the most reactive, followed by bromide, chloride, towards SN2 reaction. Okay. How about the attacking nucleophile? The nature of the nucleophile. How does it affect the rate of SN2? Now you notice in the kinetics that the nucleophile participates in the rate of the reaction. And take note that in SN2 reaction, okay, the nucleophile has to attack the carbon. And the faster it will attack, the faster would be the replacement of the halogen. Okay. So in SN2 reaction, the nucleophile should be very good. Okay. But first, in order to assess, okay, the strength of the nucleophile, you should be able to differentiate the term basicity and the term nucleophilicity. Basicity is a thermodynamic term, okay? And we talk about equilibrium here, like acidity, no? Once the reaction has reached equilibrium, you measure the H plus for acidity, no? The higher the H plus, the more acidic. Similarly, for basicity, you wait for the system to reach at equilibrium and you measure the basicity, the OH. The higher the OH, the more basic, okay? That is the term basicity. Or in the Lewis concept, the greater the ability for the compound to share its pair of electron to the acid, okay, the more basic. Now, nucleophilicity is a kinetic term. How fast this nucleophile will attack a positive carbon, just like in our illustration above, the hydroxide. How fast the hydroxide attacks the carbon, then it will become more nucleophilic. So there is a thin line between basicity and nucleophilicity, because when you say hydroxide, we classify hydroxide as a base, right? But we define nucleophile as a species having a pair of electron, right? That is capable of donating or sharing. So obviously, if the atom is negatively charged, it has a pair of electrons to donate. So the hydroxide can also act as, can also be called a nucleophile. Okay. So thus nucleophilicity parallel basicity. Well, in some cases, nucleophilicity parallels basicity. You know how to assess basicity, right? You know already how to assess basicity. The more basic, okay, a compound, see, the higher the concentration or the higher the pH, right? So does it follow that if the compound is more basic, it is also more nucleophilic? On certain cases. Which are the cases? Okay, first case. If they have the same nucleophilic centers, like in OH, the nucleophilic center or the negative center, of course, is the oxygen. So if you compare, for example, which one is a stronger nucleophile, hydroxide or water? The nucleophilic center is in the oxygen also, right? But this one is negatively charged, which we know is more basic than the water, its conjugate acid. So since OH is more nucleophilic, I mean more basic, it is also more nucleophilic. And that is true because they have the same nucleophilic centers. Same thing if you have, for example, methoxide, which is more nucleophilic, methoxide or methanol. Of course, methoxide, because they have the same nucleophilic centers. Now, that's the first case. Okay. Now we'll add one more. Say acetate. and acetic acid. The nucleophilic center is in the oxygen again, but this is negatively charged, so this will be less nucleophilic. Okay. How about if you compare two compounds with the same nucleophilic centers, like if you have hydroxide and methoxide? Which is more nucleophilic? Well, you have to assess their basicity. Which is more basic, hydroxide or methoxide? Methoxide is more basic because methyl is an electron donating group. So since hydroxide is less basic than methoxide, then it is also less nucleophilic because they have the same nucleophilic centers. Similarly, if you have acetate and you have hydroxide, they have the same nucleophilic center, but hydroxide is more basic than acetate because the conjugate acid of hydroxide is water. The conjugate acid of acetate is acetic acid. Okay. The more acidic, the weaker its conjugate base. Okay. So in acetic acid is more acidic than water. So therefore, its conjugate base, no, acetate, is a weaker base. In the case of water, since water is a weaker acid, its conjugate base hydroxide is a stronger. Okay, because that's the rule, no, according to Bronsted and Lowry. If the conjugate acid is strong, its conjugate base is weak. Okay, or if the conjugate acid is weak, its conjugate base is strong. So therefore, the acetate is a weaker base and therefore a weaker nucleophile. Again, because they have the same nucleophilic centers. Now, the second case, what will happen if they have different nucleophilic centers? But the sizes of the nucleophilic centers thus are almost the same. Like for example here, those atoms that belong to the same period in the periodic table, like carbon, ammonia, water, and hydrogen fluoride. Okay? Carbon, nitrogen, oxygen, fluorine, they belong to the same period. Although their atomic size will decrease from left to right, but the decrease is not so much compared to within a group or family. There is a very large increase in size going down. But for atoms across the period, not much. So what is the effect of this one in terms of talking about nucleophilicity or basicity? Now here, if we assess the acidity of the hydrogen here, okay, if we look at the acidity of this one, the methane, of course, is the least acidic, followed by the hydrogen and ammonia, followed by the hydrogen and oxygen. And the most acidic is, of course, the hydrogen in HF because fluorine is the most electronegative. The more electronegative, the more positive the hydrogen, and therefore more acidic, right? So let's look at their conjugate bases. To identify their conjugate bases, you have to remove the H. So the methane will become methide, the ammonia will become amide, the water will become hydroxide, and the HF will become fluoride. Okay? The weaker the acid, the stronger the conjugate base. So therefore, this will be the strongest base, followed by this, followed by this. And the weakest base now is the fluoride because its conjugate acid, HF, is the strongest. So you have this trend. So what is the trend for nucleophilicity? Now, for atoms with different nucleophilic centers, but almost the same sizes like this one, then the nucleophilicity will also be the same trend. So methyl is more basic. Then it is also more nucleophilic than the amide. Amide is more basic. Then it is also more nucleophilic than the hydroxide. Okay, so here you have different nucleophilic centers, but they have almost the same sizes. In the third case, if there is a large difference in the size, what will happen now? For example, say methoxide and methyl sulfide. The nucleophilic centers are the oxygen and sulfur. Or you have iodide, okay, and chloride. They are within the group. You have oxygen here, sulfur here, chlorine here, bromine, iodine, fluorine, in that order. So within the group, there is a very large change in the size. So what happens to the nucleophilicity or basicity if there is a very large change in the size? So let's look at the iodine, the halogen as nucleophiles. Say fluoride, bromide, iodide. Their conjugate acids are HF, HCl, HBr, and HI. Okay? So if these are in aqueous medium, okay, meaning in water, okay, the HI is the strongest acid, right, in water, not the HF, because fluorine is a very small atom. So its attachment to the hydrogen is very strong. Although it is the most electronegative, but the bond is very strong. It requires a lot of energy for the water to break it. But the hydrogen iodide has the weakest bond, although it is the least electronegative, but it can easily be ionized by the water. So that's why it becomes the strongest acid. So therefore, in water, the iodide is the weakest base. So the basicity of this one in water, therefore, okay, going down, basicity decreases, going down, where the iodide is the weakest base. So is it also the weakest nucleophile? Okay, now, this is the trend, okay, for nucleophilicity. Okay. In terms of nucleophilicity, the iodide is the most nucleophilic, increasing nucleophilicity. So baligtad. In aqueous medium, the iodide is the weakest base, but it is not the weakest nucleophile. It is the strongest nucleophile. And it has something to do with the participation of the solvent. So you have now the solvent effect for the sizes. What is the role of the solvent here? Take note that nucleophilicity is a term that is based on kinetics, no? How fast the, if this is the carbon site, how fast this nucleophile can attack this at a shorter time. So the fluoride is the strongest base. Okay. The fluoride is the strongest base. So why it's not the strongest nucleophile? The reason for that one is that since the fluoride is the strongest base and you have the water that has a partial positive hydrogen, so meaning the water has acidic, and base interact with acids. So since fluoride is the strongest base, as you can see there, this fluoride will be solvated by the water, surrounded by the water. So the water is blocking. The water is blocking the attack of the fluoride because water has a very strong attraction to the strongest base. How about the iodide? The iodide has the least attraction because it is the least basic, so it's free. The iodide is free to attack the carbon. That's why it becomes the most nucleophilic. Okay? And that happens in solvent that has acidic hydrogen. Those solvents that have acidic hydrogen are what you call protic solvents. So protic solvents like water, methanol, okay, they have acidic hydrogen, no? Okay, water, methanol, acetic acid, we can classify them as protic solvents, okay? So they can decrease the nucleophilicity of the fluoride, okay? So in other words, for bases, for nucleophiles, in SN2 reaction, you need a very strong nucleophile, right? So strong nucleophiles should be negatively charged. And negatively charged nucleophiles are also strong bases. So therefore, if you place these nucleophiles in protic solvents, the rate of SN2 reaction will slow down. So that's why SN2 reaction is not favored by, is not enhanced using protic solvents. SN2 reaction is enhanced using aprotic solvents. So what are aprotic solvents? Of course, obviously, these are solvents that have no acidic hydrogen, meaning the hydrogen is not attached to oxygen, the hydrogen is not attached to nitrogen. So like, for example, acetone is a protic solvent. There is no hydrogen attached to oxygen or nitrogen. Ether is also a protic solvent, okay? Dimethyl sulfoxide, just like ketone, except that the oxygen is replaced by S. So that is dimethyl sulfoxide. We also have furan, is also a protic, and we also have dimethyl formamide or DMF. All of these are aprotic solvents. So if you use these solvents, this will enhance the nucleophilicity of fluoride. Okay. So in protic solvents, here, if you compare fluoride and iodide in protic solvent, which is less nucleophilic or which is more nucleophilic, the fluoride will be less nucleophilic in protic solvent. But in aprotic solvent, if you compare the nucleophilicity of fluoride and iodide, the fluoride will be more nucleophilic than the iodide in a protic solvent. How you get that? So therefore, if we compare now, we have an example above, okay, methoxide and methyl sulfide. Which one is more nucleophilic? We have to identify because they have different nucleophilic centers. The sizes are quite different. So we have to assess the type of solvent. Which solvent, no? If you are comparing the nucleophilicity of this, okay, in water solvent, which is protic, then we can say that the methoxide, which is a stronger base, stronger base are less nucleophilic if you place that in protic solvent, right? So this will be less nucleophilic. But if you have, let us say, dimethyl sulfoxide or DMSO, that's a condensed part of dimethyl sulfoxide, and you compare the nucleophilicity of methoxide and methyl sulfide, okay? Now, since the solvent now is a protic solvent, then the more basic, the more nucleophilic. So this will be more nucleophilic in a protic solvent, but in protic solvent, less nucleophilic. So for iodide and chloride in DMSO, then iodide is less nucleophilic, but in water, okay, iodide will be more nucleophilic than the chloride. Okay, so there. So those are the effects of the solvents, no? So after knowing all those important properties of SN2, so basically if you have methyl iodide, no, and methyl chloride, okay, reacting with, say, methyl sulfide as the nucleophile, we expect the product, nucleophilic substitution, thio, ether, and this one also thio, ether. And what is the assumed mechanism? Of course, SN2, because you have the simplest alkyl halide. But which one is faster? Methyl iodide, you have a better leaving group, so this one will be faster than the second one, no? Now, if you have methyl chloride and ethyl chloride reacting with, let us say, cyanide nucleophile, producing acetonitrile and propanitrile. There, okay? Again, these are SN2 because methyl and primary undergo SN2 reaction, okay? But which one is faster? Okay, they have the same nucleophile, but methyl is simpler, less crowded, less steric effect. So SN2 and SN2 reaction crowding or steric effect, okay, will slow down the rate. So methyl chloride is less crowded than ethyl, which is primary alkyl halide. Then we can say that this SN2 reaction is faster. Okay. Now, if you have isopropyl chloride, okay, you react this with hydroxide in DMSO, and you react this with your methyl chloride again, hydroxide, but in aqueous medium, okay? They will produce the same product, isopropyl alcohol, okay? But SN2 reaction is faster if you use a protic solvent, because this will make the nucleophile more nucleophilic, more basic, more nucleophilic. So therefore, this will be faster than the second reaction, okay? So that is in terms of the solvent effect. So you have the nature of the leaving group, the nature of the alkyl halide, structure of the alkyl halide, and we also have the solvent effect, okay? How about the strength of the nucleophile? If you have, for example, methyl bromide, okay, and you react this with hydroxide in aqueous medium, methoxide in aqueous medium. So they have the same nucleophilic centers. The more basic, the more nucleophilic. This one will produce methanol. This one will produce ether. Both are SN2 reaction, but which one is faster? The second one, because methoxide is more nucleophilic than the hydroxide. Okay, so there, those are the SN2 reactions. So allyl, bromide, and benzyl can also undergo substitution under SN2 conditions. So you notice in SN2 conditions, the solution should be at least basic, because SN2 favors negatively charged particles rather than the neutral. Like instead of water, use hydroxide. Instead of methanol, use methoxides. So generally, the condition of SN2 is basic, because we need a nucleophile that is strongly basic also. So here, these are primary alkyl halides, right? So this can undergo SN2. As long as the condition is SN2, they can undergo SN2 reaction, producing allyl alcohol and benzyl alcohol. So these are SN2 reactions. Okay, so now let's look at the SN1, the other mechanism of alkyl halide, which is SN1. So again, for SN1, we look at the mechanism. Okay, the structure of alkyl halide, the leaving group, the nature of the nucleophile, the solvent effect, and of course the kinetics and the stereochemistry. Okay, so let's compare that with SN2. Now let's start with the mechanism of SN1 reaction of alkyl halide. So in SN1, we're going to illustrate that using tertiary butyl bromide. So if you react this with water, This will produce tertiary butyl alcohol. Okay. One thing that you would notice in this overall reaction class is, one, the nucleophile is not basic. It's usually the neutral one, the milder one. And there is a reason for that one. The second one, I use the most crowded alkyl halide, which is not reactive in SN2 reaction. Okay. So let's see why the tertiary can undergo substitution via SN1, but not SN2. So there should be a change in the mechanism. So what's the mechanism here? For the mechanism of the reaction, it involves more than one step. So it's not concerted class. It's not concerted. So the first step is you have since the molecule is too crowded, the molecule is too crowded. So the leaving group has to leave the carbon. Unlike in SN2, the halogen will not leave the carbon unless the nucleophile starts to attack. Here, the leaving group leaves the carbon, and that is obvious because it's too crowded, so it has to leave. It cannot wait for the nucleophile to attack. So there is a carbonium ion intermediate that is formed. So in the second step of the reaction, the carbon now, which is trigonal planar or sp2, will be attacked by the water both ways. It can be attacked above because it is now trigonal planar. So it can be attacked above or it can be attacked below, up or down, because you have flat trimethyl groups. So this will form now, since the lone pair will be sharing its electron, then you will have a positive oxygen like this. Okay. So finally, you will have the third step. Where the bromide has to remove this to neutralize it. So this is the main intermediate. This is a minor intermediate. And this is the final product. So if we're going to illustrate the energy diagram for this reaction, you have the energy, you have the time, So at the start, okay, this is the slow step. This is fast. This is fast also. So the slow step will have the highest activation energy. And you have a very small activation energy here for the third step. So you have the reactant here. You have the product. You have transition state 1, the rate determining step. Transition state 2, okay. You have intermediate 1, and you have a small secondary intermediate here. Transition state 3, because you have 3 steps. But this is the main intermediate, the carbonium ion. Okay? So, that is the mechanism of SN1 reaction. So if you notice here, the intermediate, the main intermediate is a carbonium ion. So therefore, one way of identifying SN1 mechanism class is there is rearrangement. You know already that if the intermediate is carbonium, there will be rearrangement, like hydride shift or methide shift. So that is one indicator for SN1 reaction. Another indicator for SN1 reaction is the stereochemistry. Now we said in SN2, if you look at the carbonium, if we let it stand, you have the CH3 here, you have the CH3 here, trigonal planar, right? CH3 plus, because the bromine has left the carbon. So you notice here that your water can attack here. It can also attack in front. Unlike in SN2, it can only attack at the back. Here, it can attack at the back as well as front. Now, what is the effect of that in terms of configuration of the final product? Well, you will not have not complete inversion. You will only observe complete inversion in SN2. Now, if the attack of the water will be at the back, similar to SN2, then you will have a product like this. Okay? If the attack of the water will be front attack, then you will have a product like this. Okay? And look at that situation there. If that carbon there, if that carbon is chiral, in this case, it's not chiral, right? But if it so happened that this one is chiral, then you will have RNS, because look at the direction of configuration. They are inverted. So if you have RNS, you will have racemization, racemic mixture. So there will be partial racemization, wherein you have a mixture of RNS. Whereas in SN2, you will have complete inversion. So that's another indication for SN1 reaction, because there will be partial racemization. Second, you have a carbonium ion intermediate, okay, which is subject to rearrangement. So these are very important indicators for SN1 type of reaction. Okay. Now, how about the kinetics? What happens to the kinetics of this reaction? Well, the rate of this reaction is dependent only on the alkyl halide. No effect on the nucleophile. That's why it's called monomolecular SN1, because it leads only to the formation of the intermediate, and the intermediate is formed from the alkyl halide. Okay. So there is no need to use a very strong nucleophile. Why do you need to do that? It doesn't affect the rate. Okay, so that's why we use a milder nucleophile, water, instead of the hydroxide, because it doesn't affect the rate anyway, only the alkyl halide. Okay, now how about the structure, the reactivity of alkyl halide to SN1? Reactivity of alkyl halide towards SN1 reaction, which is the most reactive. Now, since the intermediate is carbonium ion, anything that will stabilize a carbonium ion will lower the activation energy in the rate determining step, and therefore increases the rate. So the tertiary is the most reactive because you have 3 methyl groups that will stabilize the carbonium ion. So in SN1 reaction, the tertiary is the most reactive. So it's reverse. Tertiary alkyl halide, the most reactive, followed by secondary alkyl halide, followed by primary alkyl halide, followed by methyl. The methyl halide will no longer undergo SN1 because the methyl carbonium is the most unstable. Okay. In fact, methyl and primary alkyl halide usually undergo SN2 because they are less crowded, less steric effect, and that is very good for SN2, no? But not very good for SN1 because their carbonium are very unstable, right? Primary and methyl usually undergo SN2 rather than SN1. Tertiary definitely will undergo SN1 because it will not undergo SN2. Now the secondary is at the middle. So therefore, the secondary can undergo both SN1 and SN2. Which one will favor will depend on the conditions of the reaction. If the condition is good for SN2, then it will undergo SN2. If the condition is good for SN1, then it will undergo SN1. Okay? So let's look at that. Now, for example, here, if you have no problem with tertiary, no? But for secondary, let's say you have isopropyl chloride. You react this with methyl sulfide. Sorry. Say you react this one with methanol. And then here, you react with methoxide. Both will produce the same product, nucleophilic substitution, an ether. This one is also an ether. But the question now is, what is the assumed mechanism of the first reaction? Is it SN2 or SN1? Now here in the second, it uses a stronger nucleophile. In SN1, it doesn't need a stronger nucleophile because it's not part of the rate anyway. So methanol is a weaker nucleophile than methoxide, so most likely, and your alkyl halide is secondary, which can undergo SN2 or SN1, then most likely this will be SN1, and this will be SN2. There, okay? Similarly, for allyl chloride, this is a primary alkyl halide, right? Same thing with benzyl chloride. We said that these two undergo SN2, right? Can they undergo SN1 even if they're primary? Yes. Unlike the one here, we said that it usually undergo SN2, but this primary is quite unique because if the chlorine leaves the carbon to undergo SN1 to form the carbonium, this is stabilized by resonance. Okay, same thing with benzyl. So that's why even if they are primary, the chlorine can leave because the carbonium becomes stable. So therefore, these two can undergo SN1 also as long as you have the right condition. So if you use water, which is a milder nucleophile, then you will produce allyl alcohol and the assumed mechanism, of course, is SN1. Same thing here. Use a milder nucleophile like water, you will produce benzyl alcohol. And the assumed mechanism is also SN1. Okay. So that is reactivity of alkyl halide. How about so we have discussed so far the kinetics, the mechanism, the reactivity, and of course the nature of the nucleophile. We said nature of nucleophile, we have discussed that already, no? In SN1, it doesn't utilize a very strong nucleophile. And usually, no, if you notice, milder nucleophile, not a strong base nucleophile. Okay. Your nucleophile can still be negative, but not a strong base, like, for example, acetate. It's negatively charged, but it's not a strong base nucleophile. So if you use this, most likely the mechanism of the reaction would be SN1, no? Because it's not a very good nucleophile, very strong nucleophile. So if you react this, for example, with isopropyl chloride, then we can still assume that the mechanism is SN1. You react this, okay, acetate, nucleophilic substitution reaction. Then you will have CH3, CO. So you have an ester that will be formed for the reaction. And the assumed mechanism would be SN1. Right now, you notice in SN1 reaction that the sorry, ito class. Dapat uned, hindi pwede talagang H pa rin yan, neutral pa rin yan to undergo. Yung negative niyan, SN2 pa rin. Sorry I know. You notice in SN1 reaction that the nucleophile is also the solvent. No, like water is a nucleophile, but it's the solvent also. So if the solvent is part of the reaction, you call the process solvolysis. So for water, you will have hydrolysis. For alcohol, you will have alcoholysis. Okay. So these are very common for SN1 reactions, no? The solvent acting as the nucleophile, okay, for the reaction. Now, for the leaving group effect, the same thing, no? Yung substitution for leaving group. So iodide will still be the most reactive, followed by bromide, no? Followed by chloride. Yan. Ganun pa rin, no? Yung assessment nyo sa leaving group. Okay. And then you have nature of nucleophile. Protic and aprotic solvents has no effect, no? Because for SN1 reaction, the solvent is part of the reaction. Okay. So protic and aprotic solvents greatly affect SN2 reaction, but not much. Okay, and you have to be very careful for SN1 reaction because it will undergo rearrangement. Like for example here, if you have this is a secondary alkyl halide. So let us say you react this with water, and that is secondary. Secondary can undergo SN1 or SN2, right? Okay. So you have to look at the solvent. The solvent is milder. So therefore, this will undergo SN1. And if it is SN1, the carbonium will be here. And if the carbonium will be here, there is a tendency for this one to shift here. So there will be hydride shift. So therefore, the resulting product, your OH will be here, not on the BR, because the hydrogen will move to form a more stable carbonium. So you will end up with this product. And because it is SN1. But if you have, for example, hydroxide, so the assumed mechanism, this is a stronger nucleophile, SN2. There will be no rearrangement because SN2 is concerted. Then the substitution of the OH will be at the BR. You will end up with this product. So you see the difference in the reaction. Okay. So there, okay. Those are the SN1 reactions in terms of kinetics, mechanisms, no? And you have to be very careful for these two, especially for secondary, no? Which one will undergo SN2 or SN1 for secondary, because they can undergo both, no? Primary, usually SN2, no? Tertiary, SN1, but primary, you have to be very careful with allyl and benzyl because they can also undergo SN2 and SN1, no? So depending on the condition, like especially the nature of the nucleophile, will it favor SN2 or SN1 reaction? Okay. Now, sometimes in SN2 reaction, no, there are cases in which the leaving group and the nucleophiles are in the same structure, like this one here. Say you have a Br here and you have an OH here, and you hit this. Okay, what happens? This is the nucleophile. This is the leaving group. So you only have one reactant. What happens is that this one will attack this in a concerted manner, SN2, generating a cyclic compound. You will have now 5 central atoms. One of this is, of course, the oxygen there. And of course, you have the byproduct. So you will end up with this product. Okay. You call this intramolecular SN2 substitution reaction. Okay. So that is for alkyl halides, no? SN1 and SN2. How about alcohols? Alcohols can also undergo, okay, the same mechanism, SN1 and SN2. Okay. Now there's a difference here in terms of the reactions, but first, the classification of alcohol is similar to alkyl halides. We have methyl alcohol, okay? We also have primary alcohol because the carbon containing the OH is attached to one methyl group, or you have secondary alcohol. This is secondary. The carbon is attached to 2 carbon, or you have tertiary alcohol there, okay? And then you have the 2 special, allyl and benzyl. So you have allyl and benzyl also. Allyl alcohol, which are primary. Okay. The difference here, okay, is that if you look at the SN1 mechanism, or SN2 mechanism for this, you have methanol. There is no direct substitution because OH is not a good leaving group. It's not a good leaving group class. It's hydroxide. It is strongly attached to the carbon. So in order for this one to be replaced, we have to protonate or acidify it. And the use of hydrogen halide is perfect, like hydrochloric acid, because the acid part of hydrochloric acid will act as a catalyst to protonate the OH so that it will become a good leaving group. So instead of OH, it is now water. So it can easily be replaced by the chloride. Okay, forming methyl chloride and water. There. Okay, so you have here methyl chloride and water. Okay, so for SN2 reaction, you have a backside attack again for this one. But unlike alkyl halide, where we have a little bit of confusion for secondary because it can undergo both. But for alcohol, secondary alcohol, because look at the mechanism, it involves protonation of the OH and usually lead to carbonium ion because water will easily leave the carbon. Okay, so there is a greater tendency for the secondary alcohol to undergo SN1. So this will be SN1. Definitely this will be SN1. Only the methanol is SN2 and the primary. Okay, because the carbonium ion are not very stable. But secondary definitely will undergo SN1 rather than SN2 reaction. Okay, so take note, the OH are usually replaced by hydrogen halide, not only HCl, but you can also use HBr or HI, no, for substitution reaction to happen, no. But there are special reagents for the replacement of chlorine, of OH, not only hydrogen halide, for example here, ethyl alcohol, you can also use thionyl chloride. This can replace the OH with chlorine, and the byproduct are all gases, sulfur dioxide and hydrogen chloride. Okay, so the reaction is shifted to the right, no? Similarly, you can also use PCl5 for this one. Instead of thionyl chloride, you will also produce alkyl halide. So these are optional reagents, no, to convert alcohol to alkyl halides. Now, how about allyl? Okay, allyl alcohol and benzyl alcohol, will they undergo SN2 or SN1? They're primary. Okay, but if you add hydrogen halide here to form allyl bromide, the assumed mechanism here would be SN1. Why SN1? Because if this one is removed by the H, is the carbonium ion stable? Yes. Unlike the primary alkyl halide of alkane, this one is different because even if it's primary, it is stabilized by resonance. Okay, so that's why the OH will leave the carbon and making the carbonium stable. So therefore, the assumed mechanism is SN1. Same thing with benzyl alcohol. Okay, if you react this with hydrogen halide to do the substitution reaction, CH2Br, then the assumed mechanism is also SN1 reaction. Now, supposing your compound is an ether. Let us say you have this ether. In ether, the leaving group is alkoxide. Alkoxides are strong bases like methoxide, ethoxide, tertiary butoxide. They are strong bases. So just like OH and alcohol, they are not good leaving groups. So we have to protonate them also. So therefore, substitution of ether can happen similar to alcohol. Say if you add HCl, the H will protonate the oxygen to make it as a good leaving group. But the question now, if you have 1 mole of HCl, if this one will be protonated so that it will be removed, just like the water, if that will be protonated, and attacked by the chloride, there are 2 options for the attack. If the chloride will attack this carbon here, then this one will break away, forming methyl chloride and tertiary butyl alcohol. But if the chloride will attack this one here, then this one will leave, producing methanol and tertiary butyl chloride. So which one is more feasible? Now, if you look at the mechanism, if this one will, if the left part will happen, your methyl is the carbonium, which is very unstable, meaning it will not easily break. Whereas if you go to the right part, your carbonium is the tertiary, because the breaking will happen here. And tertiary is very stable, so therefore most likely this will be the product, okay, of the reaction. You get that? Okay, in the laboratory setting, okay, substitution reaction, like for example, conversion of alkyl halide, alcohol to alkyl halide, you use what you call Lucas reagent. In Lucas reagent, you use an additional catalyst, zinc chloride. Okay. The zinc, which is +2, can interact strongly with the OH, enhancing the removal. So aside from the H plus to protonate the OH, the zinc +2 can also enhance the removal, generating the alkyl halide. And alkyl halide are insoluble in water. Alcohol are soluble. So you can see in the test tube during the experiment if alkyl halide is formed. Because from the alcohol, if this is alcohol, you will see there will be no, say if that is pure alcohol, and then you add the Lucas reagent. If alkyl halide is formed, there is a layer. So this will be your alkyl halide that is not soluble in water. And they vary in terms of the formation. Of course, the tertiary, which is the fastest, no, because in SN1 reaction, it forms a carbonium, then it will easily appear. No, the secondary, which is less reactive, because the carbonium is less stable, it will appear after 5 minutes. The primary, which is the least, no, maybe it will take several days for you to observe that. Okay. So these are the important reactions of alkyl halides, alcohols, and ethers. Okay. And there are two important mechanisms. Take note, SN2 and SN1. Okay. So that's all for now. Okay. And the next topic would be the competing reaction, which is elimination reaction. Okay.